Good evening, everybody. My name is Srdjan Usorac, and I'm going to talk about a topic that is the application of Linux container solution in an automotive uh, environment. Basically, when talking about the automotive environment, the core sector of our interest is the in-vehicle infotainment region. The IV sector is a vehicle subsystem with driving information and consumer entertainment data, and it marks significant development in the software of the automotive in the past few years, and it usually has an Android operating system which is suited for that for the software to run on top. On the other hand, driver assistance systems, or in short, ADAS systems, usually have a Linux operating system in the bottom as a platform dependent layer. For future development, it is necessary for these two sectors, namely these two operating systems, to communicate in a certain way and share consumer quality information. That could be achieved when using two separate hardware models, but in our research, we are talking about the coexistence of two operating systems on a same SoC. A commercial solution already exists, which are the system hypervisors, which enable for the Android and Linux to coexist on the same SoC. They are existing like guest operating systems, which are running on top of the hypervisor host system, which has all of the necessary device drivers included. Also, this solution manages the integration of both IV and ADAS functionalities through standard IPC communication mechanism. And here are some pros and cons of the hypervisor solution. Some pros include, of course, the multiple guest OS support, namely here Android and Linux, but there could be more guest operating systems. Of course, it has its application in the automotive domain. Also, it introduces the shared memory, and it enables the secure communication, and also graphical information can be shared in a secure manner. On the other hand, hypervisors have a certain limitation, which include that all system resources are statically distributed across multiple operating systems. In short, we introduced here RAM memory, CPU time, also CPU cores. That's the first con. The second main issue is that guest operating systems usually have its own virtual devices allocated and pass-through devices, which utilize a lot more memory, making hypervisor systems not applicable in the limited resource systems because they allocate around 2 gigabytes just to function. Our solution is based around the usage of container systems. The container, namely Linux container systems, introduce new functionalities in virtualization the virtualization environment, which is that both guest and host operating system, in our case Android and Linux, share the same kernel, which means that it is much simpler to share data between the systems and to integrate different classes of algorithms. LXC, or Linux containers, they have a partial virtualization, which is utilized using both C groups and namespaces, which are main components of the Linux container environment. Also, in contrast to the hypervisors, which include static resource allocation, by using container systems, the resources are dynamically distributed across all operating systems, both guest and host. Regarding our solution, we managed to utilize this container technology to enable support for both Android and Linux operating system, which coexist on an automotive-grade platform. To achieve this, new functionalities were introduced and some configured. Regarding the Linux host system side, kernel was configured to support LXC container technology and to support Android low-level components, because now Android as a guest operating system relies on the host system kernel. It doesn't have its own kernel. We utilize the IV shell environment, which we use to forward events such as input and other graphical data to Android using the standard Wayland display setup. Also, what we implemented was a container manager, commonly used technology, which configures, starts, and maintains the container and the guest operating system inside it. Regarding Android, Android is now the guest operating system. Our starting point was to use a standard Android version 10 of the Android open source project, and we configured and implemented a graphics adaptation layer, which includes the configuration of the graphics engine, which is usually the component of the Android for generic background management and data rendering. Also, what we did was configured the hardware composer, which is now acting as a Wayland client for displaying data information on the host system side. The composition and all functionalities remain the same inside the hardware composer, of course.
Mr. Usorac, 1 minute remaining.
Okay, thank you. For the bridge communication, as it could be seen on this solution graph, all the communication between Android and Linux host operating system is achieved using Container Manager API. Regarding implementation, our solution is currently implemented on the Qualcomm Snapdragon evaluation board. We configured the Linux using the standard Yocto project. Android device is also configured in a standard way. And as it could be seen on this partial picture, on the bottom left side, a Linux application is being run, and on the bottom right side, an Android news application is executed. As it could be seen, both applications seem like standard host system applications, which means Android is basically invisible when implemented inside the container. Some next actions to better our solution include a comparison of the hypervisor and Linux container solution on the same platform environment, Android device optimization to gain better performance, and to introduce additional Android features such as GPS, audio, video, and Bluetooth. Thank you for your attention.
So one question, so this is the concept. So can you tell us what would be the next steps for potential improving of the proposed concept?
Yes, currently it's implemented, only the input and graphical bridge implementation is achieved. New features will be added, audio support, which will be controlled. All Android interfaces will be controlled from the Linux system side, GPS, audio, video, and same. That's one path we are going. And the other path is the optimization part, which means basically Android is a background service inside Linux environment, which means a lot of Android services are basically unused and could be shut down to achieve better performance footprint, to utilize a lot less memory and the system boot time to be shorter.